Okay, we're gonna talk about energy in this video. This is gonna be a longer video, just to warn you guys. So if you don't have time to look through the whole thing, that's fine. But it's gonna be more like a intro video, not necessarily a straight up problem working video. We are gonna work some problems, but it's gonna be the simpler problems. So energy. We're gonna talk about mechanical energy in this class. This is AP1, and really we're gonna focus on maybe two different types if you really thought about it, but really we're going to talk more about three. Um, the first type is called, well, energy of motion. And so we're going to talk about kinetic energy. And kinetic energy, we're mostly going to say, hey, it's KE for short. And kinetic energy is the energy of motion. So if something's moving, it's going to have kinetic energy, and this is going to be motion relative to something else. And, so it's this way we can say it has more energy the faster it's going, the more mass it has, and basically a lot of things, everything pretty much has a little bit of kinetic energy if you really think about it. If it's vibrating back and forth, if it is moving left or right, this pen, I'm giving it kinetic energy right now. I guess my table's getting kinetic energy. But if it's warm, those molecules are probably moving around. They're probably vibrating around, or they're shooting around like air molecules are, and they have kinetic energy. It's the energy of motion. And so there's an equation for kinetic energy, and the equation for kinetic energy is 1/2 mv squared. And for you guys in calculus, or if you go on the calculus, you'll probably remember back to this, and whenever we talk about momentum, you'll probably remember back to this 1/2 mv squared, and it's going to be kind of unique. So kinetic energy. Kinetic energy is based upon the mass of the object. It's based upon the velocity of the object, and we're going to use kilograms here, and we're going to use meters per second there. And so if we looked at the units for kinetic energy, we have 1/2, which is not it's unitless, and m is going to be in units of kilograms, and v is going to be in units of meters per second. That's velocity, and that's going to be squared. And so if we take a look at that square on the ms, m per s, that's really coming down to this: kilogram meters squared over seconds squared, as far as my unit for energy. And that's kind of a pain in the butt to write all the time, and so what they did is, in honor of this guy with the last name of Joule, they replaced this thing with the word joule, or often you're going to see this with just a J. And so in our problems, if you see a unit of J, then that means that really it's this stuff. Okay, so a kilogram meter squared over second squared. The other thing that we can say is that, remember back to newtons. If we talk about newtons, well, newtons is going to be a unit that replaces a bunch of other units. And for units of force is equal to ma. Well, m is going to be kilograms, a is going to be meters per second squared, and so really the units for newtons is kilogram meter per second squared. Well, that's very similar, right? So what's the difference? The difference is that there's another meter here, and we're lacking one there if we want to make it the same thing. So if I want to make it the same thing, then I would take newtons and I'd multiply it by meters. And so if I take this and I multiply it by another meters, I get kilogram meters squared over second squared. And so this is actually also equal to a joule. Now, if we look at this even more, newtons is force, and m in the unit form is going to be meters, so that's going to be a distance or a displacement, so maybe we'll say a d here, and this force over a certain distance is going to give us something called work. Now, we got to be very careful here, and I know I'm kind of going sideways, but that's just kind of how I'm writing, sorry. Let's see if I can't move that. Well, there you go. So we need to be very careful here, because the force that we're talking about for this certain displacement has to be parallel to that displacement. That's going to often require you to use like a cosine, sometimes a sine, depending on what angle you have. In college textbooks, you're often going to see FD cosine theta. But just remember that it's always the component that is parallel to that displacement, and that's going to be equal to work. So work is energy. It's going to give you energy. It's going to take it away if we make it move slower. And this is equal to a change in the kinetic energy of our object. So if we want to change the velocity, we got to apply a force for a certain distance on it. And that kind of makes sense, right? So if you apply a force on a car, if you apply a force on your friend, if you apply a force on your pencil or pen, then we are going to change the velocity of it. And that's, we're doing work on this object. So that's kinetic energy, and that's work for you. And we'll come back to those. Now, the other thing that we're going to talk about this thing called potential energy. And potential energy is, well, often I find that students kind of get confused on the idea of potential energy. It's not really, I don't really consider it energy. Now, you can, but it's, kinetic energy is whenever something has the energy already. Potential energy, the thing doesn't really have the energy yet. It's just the potential to get energy, the potential to move faster. All right. So potential energy, we can talk about it in the sense of potential energy due to gravity. And potential energy due to gravity, that equation is equal to mg delta h. Okay? So potential energy due to gravity is mg delta h. Now, what is mg? mg is a force, right? That's a force of gravity. What is delta h? Well, that's a distance. And so, really, that is the same equation that we just wrote down. That's over here. That's work. Right? That's work. And so gravity pulls straight down. A height is a vertical distance, and gravity would be in the same direction as that distance that you go. And so potential energy, really, it's just we're talking about gravity, the force of gravity, able to do work on an object to make it go faster. So if I were to hold, let's say, a bowling ball up here, and I gave it a certain height, well, what's going to happen to that bowling ball when I let it go? It's going to move faster on the way down, right? And the higher I raise the bowling ball, it's going to move even faster by the time it gets to the bottom. Well, why is it moving faster in the first place? Because gravity is applying a force on it, and it's applying a force for a certain distance. Now, it's also applying a force for a certain time, and that's going to be the next section on momentum. Right now, let's just stick to energy. So here we have Carl. Let's say that we have him with a mass of 5 kilograms. And let's say we have him at a height, what do you want the height to be? Let's say we have him, maybe like 2 meters. It's like in class, we're just holding him up there. And I drop him. And so on the way down, he speeds up, right? And so previously with kinematics, what you would say is, he starts off with a velocity of 0 meters per second. He gets to a certain velocity that we don't know, but we want to find out. He goes through a certain displacement, change of y. And we say, all right, let's go down 2 meters. And then you think to yourself, okay, well, there's acceleration, and let's make it negative 9.8 meters per second squared, and then you bonk yourself on the head because it's also a negative displacement. Okay? So, be careful. And then you say, oh yeah, it falls for a certain period of time, and you'd go through this process of making the list, and then you'd look at the board, you'd remember the 3 equations, and you'd say, okay, which one is going to fit here? How do I find final velocity if we don't have time? And well, one equation works out for that, and so you'd go to the equation, you'd write it down, and you'd say, all right, here it is, 2a delta y in this case, and we plug it in, and we want to find the final velocity, so we're going to square root the right side to get it. My initial velocity is nothing, so I'm not going to put anything in. I have 2, I have negative 9.8 for my acceleration, and I have negative 2 for my change in height. And those negatives cancel out, and I want to square root this if I want to find the final velocity. Right? That's pretty much what you go through and do. Well, the number that we get for this, let's just double check what we have. 2 times 9.8 times 2, and then we're going to square root that. And I get a syntax error because something slipped. 6.261. So 6.261 meters per second. And we also say, well, maybe it's negative because it's going down, but let's just keep it as 6.261. We're just going to hold that there. Okay? So there we are. We've got Carl. We've got his velocity at the bottom. We can probably find time from that too, right? Now, let's think about this in terms of energy. And we just talked about energy a little bit. What kind of energy is up here? That's potential energy. Okay? Potential energy. So it doesn't really have the energy yet, but it does have the potential to get some, right? It's got the potential. All we need to do is let it fall. So it's going to fall down, and by the time it gets down to the bottom, just before it hits the ground, what kind of energy is it going to have? It's going to have the other kind of energy, the energy of motion, which is called kinetic energy. Okay, now the other question we need to ask ourselves is, well, one energy is up here and another energy is down here. Was there a straight conversion of energy? Did we lose any energy? And then you got to think about the first law of thermodynamics that says, well, energy can't be created and it can't be destroyed. And we learned this in chemistry, right? It only changes forms. And the ultimate form is usually like heat. It usually goes to like electromagnetic radiation. And so, it all spreads out. So that's not very usable. But in terms of this problem, we've got potential energy due to gravity. We've got kinetic energy. One turns straight into the other. And so if I were to write this out, I'd say, hey, in the beginning, we've got some energy, and in the end, we've got some energy. And this is just being very formal about it. In the beginning, we have energy due to gravity. We have this mgh. And in the end, we have this 1/2 mv squared. Okay? And that's kind of neat. The energy in the beginning is equal to the energy in the end. Straight work. We were doing work with gravity. Gravity is making it go faster. It's giving it this energy. And if you notice, m's cancel out. They're on both sides. And so I have g, I have h. I want that v, so I'm going to move the half over. And that v is with a square on it, so to get rid of that, I'm going to square root it. And I get square root of 2gh. Well, that's kind of weird because that was the square root of 2gh, wasn't it? So that's kind of the same thing. And then we get the same number if you plug numbers in, I bet. Well, you have to. So let's kind of move on and let's figure something else out. Well, straighten this up. What else could we apply this to? So here's a problem. When we did this in class, I'm just going to do it again here. We've got this cliff, and some of you are enthralled with 2D motion problems right now because you think, oh, that's wonderful. We know how to do those. We don't, there's no challenge there. It's pretty easy. We've done those, and that's fine. Just remember what it was like whenever you were first doing 2D motion. You kind of were like, oh my gosh, 2D motion. I don't even know 1D motion. But you're getting better, right? It's been a couple months. So, checking this out, we got this problem. We got the initial velocity. Let's say we have an initial velocity of maybe 15 meters per second. And it's at an angle, and maybe that angle has a theta to it, and that theta is 30 degrees. Let's make it pretty easy. And we've got a height to the cliff, and let's make this cliff about 10 meters up, and this thing's going to be shot off, and it's going to fly somewhere over here, and it's going to hit the ground, and we want to find out the final velocity here. Now, energy is actually a pretty good way to go about this, because energy doesn't care about direction. Now, we can actually find the final velocity by doing traditional 2D motion, and what you would do is you would break it up into x's and y's and use sines and cosines and initial velocities and final velocities and make a list with x's and y's, and it would take you a little while. And then you got to remember that once you get down to the end, you'd find a final velocity, but then you have a final velocity in the x and a final velocity in the y, and you got to put them back together. Well, let's shortcut it. Let's actually talk about it in energy. And a lot of you during class were kind of ticked off whenever you found out that's all you had to do. Well, I wouldn't be a teacher if I didn't show you the hard way first, right? High school sucks. That's why it's high school. So, look at the energy. What kind of energy do we have in the beginning? In the beginning, we have energy due to velocity. It's got velocity. So, in the beginning, we have kinetic energy. Now, do we have any other type of energy? And what we got to look at is it up high? Does it have the potential to fall down and move faster? Because if it falls below the height that it's at, it's probably going to be moving faster than 15 meters per second. And so, yeah, we're at 10 meters. So not only do we have kinetic energy, but we also have this potential energy due to gravity. And looking at this problem, there's no air resistance, so we don't need to worry about that. So that's all the energy that we have. There's no friction. And we look down here, and down here, just before it hits the ground, it is definitely moving. So it's got kinetic energy, and doesn't have any potential. And some of you might say, yeah, it's got potential. Of course it does. Well, potential energy is mgh. Does it have any more h to go? And if it's pretty much on the ground, then no, it doesn't. All right. So at the bottom, we could say plus potential energy, but potential energy would be 0. So I'm just going to say, hey, it's all kinetic energy there. And if we look at it, we can say, all right, we have the energy in the beginning equal to the energy in the end due to the law of conservation of energy. And in the beginning, we have kinetic energy, which is 1/2 mv squared. And we're going to add that to mgh. And let's call this V1 because we have a V2 over there. Well, that's going to be equal to the final energy, and that's just going to be 1/2 mv2 squared. Okay? So now we have variables, and some of you are uncomfortable with variables, but it needs to be more okay with you. Slowly make it okay. All right? Give it a hug. It's okay. Every single term here has m. M. And so if we divide everything by m, really the m does not matter. The mass doesn't matter. It's kind of ironic every time we say that, because mass doesn't matter. All right, so we have v1 squared over 2 plus gh equals 1/2, or actually v2 squared over 2. And if I'm still looking at this, I'm going to multiply everything by 2 just to get rid of these 1/2s. And some of you might say, well, why are you doing that? Because I want to. All right, so v squared plus 2gh is equal to v2 squared. All right. Now, that's kind of neat. v1 was our initial velocity, right? That's over there. v2 is our final velocity. G is our acceleration, and h is our change in height, or in other words, a change in position. Well, did something click? Did you say, oh, well, that looks like something else that we're using. What is that? V initial squared plus 2 acceleration change in position equals vf squared. That's the equation we've been using the whole time, right? Don't get too upset about that. If you wanted to find the final velocity there, you can pretty much use this. This is the energy equation. It's pretty much the same thing, okay? But you got to learn how to use it in the first place in order to use it here. Okay, you got to learn how to use it the longer way in order to really understand it. So there you go. We got kinetic energy, we've got potential energy due to gravity, and we've got this wonderful energy equation, this conservation of energy equivalence. Okay, so that's pretty much the basics. I'm going to make a new video, and we're going to talk about springs.